And
see what we should do. Let's try this. Let's find the probability of at least 4 heads if we flip a coin 5 times. There we go. There's the question. We're going to find the probability of getting at least 5 or 4 heads, at least 4 heads, if we flip a coin 5 times. All right. What's your strategy?
Make the triangle.
Make the triangle. And how, the Pascal's triangle, I presume?
Yes.
So we start with 1 and 1, and we have a 1 on each end, and then in between we put a 2. There's a 1 on each end. In between we put a 3 and a 3. 1 on each end. In between we put 4, 6, 4. 1 on each end. How far do you want me to go, Brian? I mean, Ben.
Leave that row.
This row. And why is that the row I need, Ben?
Because you flip it 5 times, so it's the 5th row.
There you go. So that's the 5th row. Now, Ben chose to write out Pascal's triangle to the 5th row. That is perfectly okay. You have another alternative. What's the other alternative? That's right. Exactly. So these numbers, you need at least some of these numbers in this row. For this problem, you need some of these numbers. You can build the triangle to get the numbers, or you can do your, like he said, the C numbers. This is 5C5, 5C4, 5C3, 5C2. How, Becker, how long have you been back there? Since the beginning? I marked you absent.
Oh, yeah, no, I didn't.
5C5, 5C4, 5C3, 5C2, 5C1, 5C0. Okay? Now, so you can do it however you want. All right, what's the next step? All right, so we got the numbers we need. Okay, what's the next step? Well, which of these numbers do I need?
4 heads. At least higher
So
heads.
what might this number stand for?
That would be 5.
That would be 5 heads
0 tails.
and 0 tails. This one would be
4
heads, 1 tail.
That was delicious.
And you could go on down the line, but these are really the only 2 you need, right? Because it says at least 4 heads.
Yeah.
So we got a 1 and we got a 5. All right, so those are the 2 numbers I need out of this row. So if you did it with combinations, 5C5, 5C4. All right, then what?
5 1/2 to the 4th.
Next to each of these numbers are 2 probabilities. The probability of getting ahead and not getting ahead. And, since it's coin toss, the probability of getting ahead is 1/2, and the probability of getting a tail would also be 1/2. We want 5 of these and none of those, right? You said 5 heads, no tails? How about this one?
1/2 to the 4th.
1/2 to the 4th, 1/2 to the 1st, because that's what? 4 heads, 1 tail. So I can calculate both of these 2 numbers, this number and that number, and then what do I do with them? Add them. So that would be the answer to the question after you get it all multiplied out. Okay? We've thrown that off, so we're not digging all period. All right, now that's a little review problem. Keep track of these review problems so when you start studying, you'll have it. Okay. All right, let's just start at the beginning. You guys studied these last year. When I say sequence to you, what do you think of?
Sequence.
Yeah, when I say sequence, like a sequence of numbers, what do you think of?
Order.
Okay, like a pattern, order. Okay, give me an example.
3, 6, 6, 9.
3, 6, 9, 12, 15, and so on.
Jesus,
Beautiful.
Screw your 3, 6, 9. I'm going.
That kind of a sequence, first of all, how's he generating it? What's going on? How are we getting from term to term? Goes up by 3. So basically we're just adding 3, right? That kind of sequence where you get from term to term by adding the same number
Arithmetic.
is called arithmetic. This is an example of an arithmetic sequence. What is an arithmetic sequence? A sequence in which you get from term to term by adding the same number. In this sequence, we are getting from term to term by adding 3. That is called the common difference. The number that you add is called the common difference. And in this problem, it's 3. It's called the common difference because if you subtract consecutive terms, you always get the same thing. You get the common term. You get 3. 6 minus 3, 9 minus 6, 12 minus 9, 15 minus 12, and so on. Now, this one is kind of easy because it's basically the multiples of 3. Can somebody give me another example of an arithmetic sequence that maybe isn't quite so obvious as that one? Can somebody give me another one?
2, 4, 8.
Okay, well, let's look at that guy for a minute. We'll talk about him in a minute, but he's a whole different ball game. What's going on there? We are not adding the same thing to get from term to term. What are we doing?
Multiplying.
We're multiplying. Now that's
Word.
special too, but that's called a geometric sequence because we get from term to term by multiplying. And what are we multiplying by? 2. And that number is called the common ratio because the ratio of terms is common, is the same. All right, so we'll talk about that in a minute. Let's go back to our arithmetic. Can somebody give me another example of an arithmetic sequence?
1, 2, 3, 4.
Okay, that's another really obvious one. Let's bring it down a little bit.
200.
How about this one? Is that guy arithmetic? Yes, he is arithmetic. He has a common difference of 7. Now, your job, one of your jobs, is going to be to take a sequence like this and to find the 52nd term. The notation we use for that is A sub 52, A sub 52. That means the 52nd term. Now, what's one option you always have? Just keep going, right? That's always an option. You can sit there with your calculator and do plus 7, plus 7, plus 7, and just keep going like that. That's always an option. But maybe there's a more efficient option if we stand back and think about it for a second.
52 times 7.
The first term was 2. How did we get the second term? We added 7, right? Now how did we get the third term? We took this one and we added another 7. So we took 2 plus 7 and we added another 7, so that was 2 plus 2 sevens. How did we get the fourth term? We took this one and we added another 7. So it was 2 plus 3 sevens. Now let's look at this for a second. The fourth term was 2 plus 3 sevens. The third term was 2 plus 2 sevens. The second term was 2 plus 1 7. Is there a pattern there?
Mm-hmm.
What do you think the 52nd term might be?
2 plus 51.
Plus
7.
51 sevenths. Bingo, you got it. Whatever that equals, that will be the 52nd term. So in general, to find the nth term, to find the 52nd term, what did you do? What's this?
A1.
That's the first term. So you took the first term. And what did you add to it? What's the 7? What's the 7? That's the common difference. So we added the common difference times, okay, now for us it was 51.
Whatever that number is, n.
Whatever that number is,
Minus 1.
minus 1. 1 less than that number. Remember, we added 1 less than that number. This is the formula for arithmetic sequences. It will find whatever term you want of whatever arithmetic sequence you have. So, if you're walking down the hall and you find a sequence that looks like this, and you want the 100th term, it's easy. Is this arithmetic?
Yeah.
What's your common difference?
-2.
-2. So the formula says, okay, here we go, 5 plus -2 times 99. You'll work that out, and that will be your 100th term. Easy as can be, right? Now let's talk about this guy now, geometric. The common ratio for this one is 2. Can anybody come up with a different geometric sequence? Come up with a different one?
3, 12. 27.
Yeah, you guys, you're too obvious. Let's get a little wild and crazy.
That's what I was trying to do.
How about maybe let's start with 3 and go to 12? And then 48. Okay. Now, is this geometric?
No.
Yes. And its ratio is 4. Now, I wonder if there's a formula like this
Probably not.
that would work for geometric. Now, keep in mind, that formula is only going to work if the sequence is arithmetic. So, if I want to find the 100th term of this guy, which by the way, it would be pretty big, the 100th term, I wonder if there's a formula. Well, let's analyze it. The first term is 3.
Yeah.
The second term is found, I know it's 12, but it's found by doing what?
3 times 4.
3 times 2. The third term is found by taking 3 times
4 times 4.
4 times 4, which is 3 times 4 squared.
Yeah.
So let's look at this one now. The first term is 3 times no 4. The second term is 3 times 4 to the first. The third term is 3 times 4 squared. Any idea what the nth term might be? The first term times the ratio. So the n minus first. Very good, Maggie. That's exactly right. In our sequence, the 100th term would be 3 times 4 to the 99, wouldn't it?
Yeah.
So this is your sequence. Now that's going to be a huge number.
So we'll do it.
Okay.
Don't do it.
A couple of interesting stories here, having to do with geometric
that's too big.
sequences.
No.
One of my first years teaching, let's see, she was in a class of 87, so it would have been, she was a sophomore, so it would have been like 84, 85. This little girl who was brilliant, I mean, I knew she was brilliant, everybody knew she was brilliant. Well, I'll tell you who it is, Mrs. Bradshaw, her sister-in-law, Kathy. She's a doctor now, wonderful, wonderful family. Anyhow, Kathy came in, she was in my second year algebra class. She came in one day and she said, Mrs. Ford, my dad and I were watching TV, and they said something that it just doesn't make sense to us. Can you explain it? And I said, okay, what is it? Let's talk about it. She said, well, they said that if you put one checker on the first square of a checkerboard, you put 2 on the next one, 4 on the next one, 8 on the next one, 16 on the next one, and so on. So see what's happening? 1 checker on the first square, 2 on the next square, then 4, then 8, then 16. By the time you get to the last square on the checkerboard, you'll have enough checkers to reach the nearest star. She said, Miss Ford, the nearest star is the sun, and it's 9.3 times 10 to the 7th miles away. That would be a lot of checkers. So I said, okay, let's talk about it. Let's figure it out. What is this?
Geometric sequence?
It's nothing but a geometric sequence. How many squares are on the checkerboard?
1, 2,
36.
8 times.
36.
There's 64.
Oh.
64. It's 8 by 8, so there's 64. So what we really want to do is come all the way out here to the 64th term, right? That's the checkers we're talking about. So for this sequence, I just erased my formula, just erased it, but it's geometric. What would the 64th term be?
1
The first term times the ratio, what's our ratio?
2
2 to the 63rd. Okay, so type in 2 to the 63rd. Keep in mind that
That's a big
represents how many checkers are on that last square, right?
Our checkers in
Okay, there's a lot of checkers on that last square. But let's think about it. How many checkers do you think we could get in an inch?
2.
2?
1.5.
I think at least 2 probably.
No, I don't
3?
know.
Let's
Checkers
say-
vary in
Let's
size.
just go err on the big side, let's say 3. Probably we can't get 3 in an inch, but let's just suppose we can. So let's divide this by 3, and that number would tell me how many inches worth of checkers I have. So let's see, what might I do next? Divide by 12, and that would tell me how many feet of checkers I have. And then maybe I would divide by 5,280, and that would tell me how many miles of checkers I have, which is 4.85 times 10 to the 13th miles
Yeah.
of checkers on that last square. Now keep in mind, the sun is 10 to the 7th. This is almost that square. Not quite, but almost that square. That's a lot of checkers. Isn't that amazing? Here's another story. This is from my first year of teaching. I'm not so proud of this one, but it happened. Kind of interesting. I'll share it. Harvey will get a kick out of this because it involves a wrestler. I'm a brand new teacher, 22 years old. Going to set the world on fire. Going to change all these young lives. Didn't work out very well. First year. Kind of hard year. Had a rough group. College prep, first year algebra. We didn't call it college prep back then, we called it regular, but it was like college prep, first year algebra. 36 of them, grades 9 through 12. I had one senior in that class. And they ate me alive on a daily basis. But I had this one young man who was a wrestler, very proud of his physique. And in my first year, I had just come from the farm, grew up, on the farm. And so when the kids misbehaved, I would say, all right, give me 5 push-ups, or something like that for them to do. Well, he got to the point where he was purposefully misbehaving so that he could demonstrate his athletic prowess. So finally, I got to my wit's end. It was like, I can't do this anymore. So he was a sophomore, and so I said, okay, we're going to make a deal. And we went down to the dean's office. Mom came in. We drew up a contract because I was crying every day. He was driving me crazy. He wasn't learning math. It was just not a good deal. So I said, okay, we're going down to the dean's office. This is what we're going to do. You have to come to class. It's a law. But as long as you're quiet and you don't disrupt anybody else, I don't care what you do in class. You don't have to do any homework. You don't have to take any tests. You don't have to take any quizzes. You don't have to do anything except come to class. That's the law. Other than that, as long as you don't disrupt, I don't care, sleep all period. Doesn't matter to me. As long as you can keep this up. Day 1 of the contract, you do 1 push-up. Day 2 of the contract, you do 2 push-ups. Day 3, you do 4. Day 5, and so on. As long as you can keep that up, I don't care what you do in class, whatever you want is fine. But as soon as you can't keep up anymore, then you have to start behaving like a normal student. And that means doing your homework, paying attention, behaving. We're not having any more of these shenanigans. The dean of students, I'll never forget, this female at the time, she said, Lisa, are you sure you want to do this? I said, yes. Because what did I know that the kid didn't know?
Geometric sequence.
Geometric sequence. So it didn't take very long until this fine young man, and he did, I will have to say, he lived up to his end of the bargain. We signed all the paperwork, everybody signed it, everything was good. First few days, he slept in class and sat there, you know, enjoyed himself. And then it all came crashing down because you can see it doesn't take very long until you get, these numbers just get unmanageable.
How many days did he go?
You know, I can't remember. Was it 9, maybe 8, something like that?
Yeah. So like, he wasn't just this kid sweating in the corner.
Yeah.
No, he had to do them after school.
Oh, okay.
Okay. All right, so we're good on that. All right, so we got our formulas for arithmetic and geometric. Now, there's one more piece of this that I need you to understand. So I'm going to put a couple sequences up here, and I want you to look at them carefully. One of them we've kind of already talked about. Okay. All right, so I want to look at these 2 sequences right here. They're kind of similarly related. They're not exactly the same, but you definitely see the pattern in both of them, right? I want to talk about their end behavior, though. What ultimately happens to these sequences? What's going on with these numbers? As we go farther and farther and farther out in the sequence, what's happening to these numbers? Well, you're adding 2, so they are getting bigger and bigger and bigger. So if you started, like if you drew a number line, and you started plotting these points, like here's 2, and here's 4, and here's 6, and here's 8, what would happen as you plotted? You would just keep going and going and going. That is called a divergent sequence. It diverges, it shoots off into space. There's nothing capping it or containing it.
Is this vocab important?
Yes.
Yes.
Everything I say is important, Eudor.
That's true, but you have to make a hierarchy at some point.
Now, how about this one? What's happening here? Think about these points.
Times 2.
Well, actually,
Times 1/2.
you're actually multiplying by 1/2. You're multiplying the denominator by 2, but the whole fraction is getting times by 1/2. So what's happening to these terms? Now think about this for a minute. They're getting smaller and smaller and smaller. Now, if I were to graph them on the number line, would they just keep going smaller, 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 smaller? Would they just keep going forever and ever and ever? Actually, no, they won't. They're heading toward 0. Are these terms ever going to pass 0 and become negative?
No.
No, you're multiplying by 1/2. But are they getting closer and closer to 0 as you plot them? Yes. This is called a convergent sequence, and it has a limit of 0. Now, the notation is important also. Now, first of all, what's the difference now between convergent and divergent? What's the difference?
Where it's headed.
Divergent means it just shoots off into space. It could go that way or it could go that way. It just goes. It doesn't have a wall it runs into. It doesn't head toward a specific number. It just keeps going. What does convergent mean? It runs into a wall. It has a number that it approaches. Now, if you're convergent, then you have a limit. Okay? The limit is the number that you are approaching. So you figured out, you didn't need any fancy notation or vocabulary, you just figured out with your common sense that this sequence is heading toward 0. The terms of this sequence are the powers of 1/2. So if I let n be 1, I get 1/2. If I let n be 2, I get 1/4 and 1/3 and so on. So this says, as you let n, the power, get bigger and bigger and bigger, have I told you my sign story about the sign that used to be by the clock? I just saw Jessica look at the clock. Time will pass, will you? Yeah.
It hurts kids' self-esteem. So
That's
they
right.
know.
But I'm not worried about hurting your self-esteem. Don't look at the clock. N gets bigger and bigger and bigger. The terms of the sequence get smaller and smaller and smaller. They head toward 0. What about this one? Now, you can see the pattern. You can definitely see the pattern, right? The numerators are going up by 1 and the denominators are going up by 1. So if I said to you, what's the next term, you would all say?
15, 14.
Yeah. Now, this is not arithmetic or geometric. You see the pattern, but it's not arithmetic or geometric. We're not going up by the same amount, and we're not multiplying by the same amount. But the question is, divergent or convergent? Are these numbers getting bigger or smaller? If you have a question, take your calculator out and look at the decimals for these. Sometimes it's hard to tell with the fractions. So this one would be 1.1. This one would be 1.09. This one would be 1.08. What appears to be happening, kids? It's getting closer to 1. So this one has a limit of 1. And let's see. Would that be right? Yeah, I think that's right. That has a limit of 1. So it is convergent. If it has a limit, it's convergent. What does divergent mean?
No limit.
No limit. It means it shoots off into space somewhere, somehow. All right. Now I want to look at this one. I have not written out the terms of this sequence. This is what you did in last night's homework. You took an expression like this, like maybe it had this in front of it or something. You took an expression like that, and you were to write out the terms. Okay, so let's write out the terms. Let's let n be 1. What does this equal when n equals 1?
4.
Well, 4 on top, but, so it's actually -4, isn't it? What does it equal when n equals 2? Well, it can't, so I gotta leave that one blank. You can't put a 2 in here. Does everybody see that? But that's okay. Now put 3 in. What do you get when you put 3 in? 10 over 1, you get 10, right? What do you get when you put 4 in? 13 over 2. Make a little room here. What am I up to? I put 4 into 95.
16 over 3.
16 over 3. Next term, that'd be 6. 19 over 4. All right, write out as many as you need. Your job is to tell me, does this converge or diverge? And if it converges, what's its limit? Write out as many terms as you need. What would be the 100th term? What would be the 100th term? 301 over 98. What would be the 1000th term?
3001.
3001 over 998. Let's type these in. For this part, let's not even worry about this part, but let's look down here. What happens as n approaches infinity, as n gets to be a big number? What's 301 divided by 98? 3.07. What's 3001? Oops, 3001 divided by 998. 3.007. Any ideas? It's approaching 3. So the question was convergent or divergent? Convergent. If convergent, what's its limit? Its limit is 3. I try this one.
So how did you get -4?
Plugged in 1. Remember, when we do limits, that's a good question. When we do limits, we're talking about what happens as n gets really, really big. We don't really care about what happens over here. We want to know what happens at the end. Does the sequence shoot out into space at the end, or does it approach something in the end? We really don't care what happens at the beginning. Now, what you do in this one right now, quickly. Your job, convergent or divergent? If convergent, what's the limit? So, do what we did. Write out some terms. See what you come up with. If you were listening to me, maybe you're skipping the first few terms. I think I'll just do the 10th term. And the 10th term would be 32 over 36. And then maybe I'll do the 100th term. And maybe the 1000th term. What's happening to those? I'll do the millionth term. Well, I don't know. I don't think some of you are helping me here at all, so I went ahead and did the work myself. And I simply let n be bigger and bigger numbers. And I stuck with numbers that were easy to work with, like 1,000,000 and 1,000,000,000. And then I looked decimally at what came out. What do you think? What do you observe? This was 1,000,000,000. This is when I put in 1,000,000,000. So this is a long way out on the sequence.
It's equals to 1.33, which is the top.
Oh my gosh. She has discovered the trick. She said, you know what,
That is
Mrs.
too
Ford?
high.
I could have told you from the beginning that the limit as n approaches infinity of 4n minus 8 over 3n plus 6 is 4/3, 1.33333. How do I know that? Because I looked at these coefficients, and that fraction reduces to 4/3. Now, why does that work? Think about it. We're going to infinity. In terms of going to infinity, how big is -8? Totally insignificant. How about 6? Totally insignificant. So if these have become insignificant, then the only important part of the problem is that right there, right? That's like 4 billion over 3 billion. That reduces to 4/3. Could we have done that in this problem? What did we say the limit of this one was? 3? Could we have done the same thing? Absolutely. Right there is your limit. These numbers don't count if you're talking about going to infinity. 3n over n is 3. What's the limit of this one going to be?
1.
The limit of this one will be what? Watch it. Negative 2/3. The limit of that one is negative 2/3. Because the only part of the problem that matters is that part right there. You will spend an immense amount of time in your calculus class talking about limits. I want you to look at these three real quick here before we run out of time. Okay, very similar problems. Number one, you better be able to tell me the answer. What's the answer to number one? 3/4. The limit is 3/4. Now, number two, what's different about that one? We haven't looked at any like this. What's different about it? It's got a squared term on the bottom. Now, here's the rule. Well, here, first of all, just think about it for a second. If you're letting n go to infinity, that means you're letting n get to be like 1 billion. Would 3 billion plus 5, would that be a pretty big numerator? But how about 4 times 1 billion squared? That's way bigger, right? That's a lot bigger. So if you have a fraction where the denominator is a whole lot bigger than the numerator, what's that limit going to be? 0. When the denominator grows faster than the numerator, then the fraction is going to get smaller. What happens here? There is no limit. This is divergent because the numerator and the denominator are not growing at the same rate. Which one is growing faster? The top. And when you have a fraction where the top is getting bigger than the bottom, then the fraction gets bigger, doesn't it? and that means it's divergent. As long as the powers match, you just balance out the coefficients, 3/4. If the powers don't match, then it matters where the big one is. If the big one's in the bottom, the limit will be 0. If the big one's in the top, there will be no limit. Okay? Your first calculus lesson of your life. How cool is that? All right, your homework tonight, I will have that updated. If you check it before the end of the day, it's what's posted for tomorrow. But I'm gonna fix it by the end of the day, okay? Thank you.
I'm gonna be